Hi there everyone, welcome to my channel. This is a small demo on simulating a fake quantum computer with Numpy using Numpy arrays and matrices, concepts of linear algebra and vector spaces. It's feasible to mimic a quantum bit or qubit. In this session, I'll cover single qubits and standard basis, the building blocks of the quantum information or data. I'll cover single quantum gates, also called local gates. And within this family, I'll cover Pauli's gate or XYZ gate and Hadamard gate, the superposition gate. Finally, I'll cover CNOT gate, aka control NOT gate. It's also called CX gate sometimes. It enables interaction between two qubits. It's also called non-local gate or at a distance gate sometimes, from Einstein's famous spooky action at a distance. This gate is used in the construction of multi-qubit gates like CC0 for control NOT, and also called Toffoli gate, and swap gates, and many more. It's widely used in the generation or creation of quantum entanglements like Bell pairs. It's also used in GHZ circuits. It's not possible to convert a digital computer into quantum computer. Reason being, they are a different computational paradigms. Quantum computer uses principles of quantum physics like superposition, entanglement, interference to process the information. So these things cannot be achieved using a digital computer, no matter how evolved your computer is, be it a supercomputer or hypercomputer. You cannot turn it into a quantum computer at any cost. Without further ado, let me show you the simple code. Okay, let me open the project first. Opening the terminal. Now the Jupyter IDE. And here we go. So CX IPython notebook has the NumPy code, and this is Qiskit. I'll first demo the NumPy followed by Qiskit. From NumPy, I'm importing arrays, matrices, matmul for matrix multiplication, cron for Kronecker product, dot to define the inner product, outer to define outer product of two matrices or projection, diac for diagonal matrix or to define a diagonal matrix, I for identity matrix, linealc for linear algebra. Though I may not be using some of these libraries in this session. Now define the single qubit. So qubits carry quantum information, and they are real, physical, tangible in nature, and they are also available in the form of hardware. For instance, IBM Qiskit, Penny Qcode, Xanadu. These are some well-known platforms or cloud computing platforms who provide quantum computing as a cloud solution. A logical qubit is a mathematical abstraction of a physical qubit, and the complete discussion and comparison is out of scope of this discussion. Now define the qubit states and standard basis. Qubit states are represented using linear algebra from Hilbert space, and the basis vector provides the fundamental building block of quantum information. So they form the fundamental, quantum information, just like zeros and ones form the entire binary, or define the entire binary computers. There are three basis vectors in standard basis. The first one is z basis, and in NumPy we define ket0 and ket1 in this fashion. It's a column matrix, and this is a logical equivalent of ground state of a physical qubit, and ket1 is the logical equivalent of the first excited state of physical qubit, and this is the very definition. Similarly, we can use matrix just like matrix. However, I'll stick to array, and the shape of this ket0 is 2 cross 1. It's a column matrix or column vector. Orthonormality. One of the important criterions, the basis vector should satisfy is orthonormality. Orthonormality is the combination of orthogonality and normality. Let's say x and y are two vectors. If the inner product is 0, that is bra of x with ket 0, bra of with ket x, ket y is 0, we call it orthogonal. Essentially they are mutually perpendicular, and if the inner product of the vector with itself is 1, we call it normality. And here is the check. So the inner product of ket 0 with itself is 1 and ket 1 with 0 is 0. This makes so here the magnitude is 1 and here the dot product is 0. Normality check. So this is also one way of checking normality, or we can even use this lin elch dot norm of say ket 0. And now the x basis. So there are two pairs again, so ket plus and ket minus. So ket plus is defined as a linear combination of state ket 0 and ket 1 over square root of 2, and ket minus is defined by ket 0 minus ket 1 over square root of 2. So the difference is that there is a local phase between the two states. Ket xp is defined in this way by dividing it with the magnitude of both the vectors, and ket xm in this fashion. Now orthonormality. So the inner product of plus state with minus or minus state with plus is 0, and here is the validation point, and the norm of ket xm for instance is 1. We can even check for ket positive, that is ket plus. Apparently it's 1, and the inner product of the plus state with itself or the first superposition state with itself is 1, or ket xm or ket minus with itself is 1, and this is the magnitude of the state. We use the norm from linear algebra to define to calculate the norm of vector. And finally y basis. Y basis is defined in this manner: I plus and I minus, and this is the representation. So it's a linear combination of ket 0 with ket 1 with a plus or minus I in between. So that's the phase of 90 degrees in general, where I is under square root of minus 1. And ket yp is the positive part of it. It's a linear combination of ket 0 and ket 1 with a complex, this is the Numpy or Python representation, and divided by magnitude of square root 2, the same as the Hadamard x ket plus or ket minus states. The fundamental difference is this phase factor. Like x basis and y basis, like x basis and z basis, it too satisfies the orthonormality criterion, and this is the validation check. Single qubit states. Gate is an operation in quantum computing that transforms one qubit state into other qubit state. Gates are also called operators. They transform or process information. Polis gate. It's a single qubit gate, has a dimension of 2 cross 2, and the first one being X gate or X operation, and using Numpy array we define the matrix in this fashion. Polis X gate is also known as bit flip gate, as it is similar to that of binary NOT gate, which transforms 0 to 1 and 1s to 0. Likewise, ket 0 is being transformed to ket 1 and ket 1 is being transformed to ket 0 with the use of Polis X gate. That's the very reason why it's known as bit flip gate. And to know the shape of the matrix, we use the accessor shape, and here is the shape of the X gate and now Y gate. And using Numpy array, this is the very definition, or this is how we define the Numpy, this is how we define the Y matrix or Polis Y operator, where J is imaginary number in Python And now the Z gate or Z operator. This is also called a phase flip operator. This is unlike bit flip. This does the phase, and there is no equivalent of phase operator in digital computer or digital world. And the shape of the Z operator is 2x2. Now let's look into some of the important features or attributes of Polish gate, properties of Polish gate. It's a unitary gate in nature, and this is the very definition of unitary operator. And here, instead of matmul, I use at the rate. We can use at the rate to define the matrix multiplication. Star or asterisk is a element wise multiplier, whereas at the rate is the matrix multiplication. It performs matrix multiplication of two matrices. And you can see here, when A transpose of A is identity, likewise X transpose of X ended up with a identity matrix here. Hadamard operation or gate, and this is the matrix definition. There is no equivalent of Hadamard gate in digital computers or Boolean algebra. This is completely out of the world and a gift from quantum computing. Hadamard gate is also known as superposition gate, as I said. And let me show you, when Hadamard is operated on ket 0 or the ground state of qubit, we'll end up with a superposition state, and this is equivalent of ket plus 1. So at the rate is a matrix multiplication. This is not like X or asterisk is an element wise matrix multiplicator, whereas at the rate is a true matrix multiplication. We can also use in place of matmul, and they both yield the same result. And here is the validation point to prove that when Hadamard is operated on ket 0, we end up with ket x plus or ket plus state. And now let's operate Hadamard on the first exerted state of a qubit, that is ket 1, and we'll end up with a negative superposition state. In fact, you can validate it for yourself. Let me copy this, put it here. Now it should actually return 0 or false, obviously. Now let me change it to XM. That's it. There we go. So it's a negative superposition state or ket minus. This is ket minus, in fact. Now single qubit operation. In this, let's operate X operator on ket 0 or the ground state of a qubit. We'll end up with ket 1, which is the first excited state of a qubit. And when it is done on the first excited state or ket 1, we'll end up with 0 or ground state. Thus, it's also known as bit flip gate. And here is the proof, or here is the validation. So ket x is operated on ket 0, and we'll get similarly ket x is operated on ket 1. We'll end up with the ground state, and this is the validation. Moving on, Hadamard is when operated on ket 0, we'll end up with this state, and when operated on first excited state, we'll end up with the superposition state. And here is the proof. And you can validate these things for yourself. And now 2 qubit states. I prefer big endian notation, where the most significant bit is on the left hand side, whereas the least significant bit is on the right hand side, or MSB is always on the top and least significant bit always on the bottom. Two qubit states are also called multi-qubit states. They can be generated using the Kronecker operator or cron from Numpy. And this is the mathematical notation of a Kronecker product. So to define a Kronecker product of two matrices, we use this symbol, essentially meaning Kronecker product, and also written in Dirac notations in this fashion. For instance, ket 0 0 is a Kronecker product of single qubit ket 0 with itself. Similarly, you can generate multiple Kronecker products or multiple states, or instead of two states. For instance, I define ket 0 0 using this cron operator, ket 0 and ket 0. This is for, and ket 0 1 in this way, and ket 1 0 in this way, and ket 1 in this way. So this is equivalent of 0, this is equivalent of 1, this is equivalent of 2, and this is equivalent of 3, because it's a 2 to the power of 2. And the Kronecker product of two matrices having dimension 2 cross 1 yields 4 cross 1. So here is the proof. When we so the Kronecker product, or let's say the dimension of ket 0 or ket 0 1 or whatever, so the dimension is 4 cross 1. I can also show you for the other one. It should be 4 cross 1, or we can also do for the ket 1 0, for example, it's 4 cross 1. CNOT operator or gate. This is the standard schematic of CNOT gate. The top line is called source qubit and the bottom one as target. In big endian notation, in little endian notation of, however, it flips. CNOT gate is a unitary gate, and this is the very definition of a unitary matrix. Given A is a n cross n matrix, so the product of transpose of A with A is identity. That's the mathematical definition. CNOT gate, as we discussed in the beginning, it's a 2 qubit operator. It actually transforms, or it interacts between 2 qubits. Unlike classical counterpart, it can perform the entanglement. So let me show you the classical CNOT versus quantum CNOT. On the right hand side, this is a CNOT operator in Boolean algebra, and this is the truth table. On the left hand side, however, we have the quantum CNOT. The difference is that this is applicable for the digital or Boolean algebra, whereas this works on quantum domain or quantum data. The other point is that this cannot perform the entanglement, whereas this can. It's a non-local gate from Einstein's famous spooky action at a distance. This is also called at a distance gate sometimes. It can perform the bit flip, however, in a controlled mode. So this is more or less like X gate, but in a different fashion. X gate is applicable for a single qubit, whereas CNOT works for 2 qubits. And this is the matrix representation of control NOT gate. I am using the CX notation here. Now let me show you a small, as you see here, so it looks similar to identity matrix, except for the second, from this row onwards, and this column onwards, we see the difference. So this is X matrix. Until here, it's an identity, and from here, it's actually an X operator. So this can be, it can also be represented in this fashion. You can assuming identity. This is I. This is 0 or 0 matrix, and 0 matrix, which is a 2 by 2 matrix itself. And here we have the X operator. So this is a 2 cross 2 matrix. In a general understanding, it's a 2 cross 2. and this is a 0 matrix of 2 cross 2. Similarly, this is 2 cross 2. It's again 2 cross 2. It's a unitary gate. So using this first definition or first identity, so if I do the transpose of C0 matrix and multiply it with itself, so I'll end up with an identity matrix. This proves the unitary property or unitary property of C0 gate. And here is the validation point. Now let's operate Cx gate or C0 gate on 2 qubit states. As you know, it's a 2 qubit gate, so I cannot operate it on single qubits. Therefore, I had to construct 2 qubits and then operate C0 gate. So when I do the Cx, or let's say the C0 operation on state 0, 0, or on 2 qubits having state 0, 0, I'll end up with no change. And this is the proof, or this is the validation. Again, when I do the Cx operator on ket 0, 1, first or the source qubit being 0, 0 and or in 0 state, and first or target qubit in the first state or excited state, I'll end up with no change. And here comes the magic. When it is operated, when Cx is operated, or let's say C0 is operated on ket 1, 0, where source is excited state and the target being in ground state, I was expecting no change. However, I'll end up with a wrong answer here. And however, so this state, the property of C0 gate is to flip the second qubit or the target qubit, because it's 1, so it flips this qubit to 1, not operation or X operation. So you will end up with ket X 1, 0 operating, the Cx operating on ket 1, 0 will end up with ket 1, 1. So the target qubit is being flipped by the first qubit with the Cx operation. And here, and this last one being Cx gate being operated on 1, 1. That is, the source qubit, both source qubit and target qubits are excited, are in excited state. So I was supposed to expecting it no change, but ended up with wrong result. So this is the true result or correct result, because the source qubit is in the first in the first excited state, it will flip or it will rotate the target qubit into 0 state. Apparently this is true. So in some binary sense, when C0 operates on 0, 0, we'll end up with 0, 0, and C0 operates on 1, 0, the left hand side qubit being the source qubit and right hand side qubit, the right hand side qubit being the target qubit, will end up with 1 to 1. And similarly, when C0 is operated on 2, we'll end up with 3, and when C0 gate is operated on 3, we'll end up with 2. All this is from target qubit side. Therefore, Cx or C0 gate actually does the addition modulo 2.